This is British Mathematics Olympiad 2000, round 2, question 3, and we are trying to find two positive integers a and b, which have the property shown that a to the power of the third plus b to the power of the third minus 1 all squared will equal 49 plus 20 times 6 to the power of a third. And so the first thing we shall do is to multiply out the brackets on the left-hand side. And this produces the result shown on the left-hand side here. And we can see that we can take one off both sides to neaten things up a bit and then consider what the expression is telling us. Now, the key to this whole problem is given by considering where we're going to get this 48 from. Because if we look on the left-hand side, we've got a to the power of 2/3, b to the power of 2/3, and then subtract a to the power of a third plus b to the power of a third twice, and then we have plus 2a to the power of a third, b to the power of a third, and it must be from this bit, 2a to the power of a third, b to the power of a third, that we're going to obtain the number 48. And the only way that can be done is if we can involve the two numbers 6 to the power of a third and 6 to the power of 2/3, and you'll probably see that a bit more clearly when I write out the next line. And so I have said that a to the power of the third is the same as p times 6 to the power of a third, and that b to the power of a third is the same as q times 6 to the power of 2/3, and that is the only way we're going to get the number 48 out of there. And I've separated that part down at the bottom there. 2 times p times 6 to the power of a third times q times 6 to the power of 2/3 equals 48. And so we shall consider this further and what the rest of the expression is telling us. And so you can see that I have underlined in blue a to the power of the third equals p times 6 to the power of the third, and b to the power of the third equals q times 6 to the power of 2/3, and I have substituted those two values into the expression on the left-hand side, and I've tidied this up a bit, 2pq, q to the 6. I've now made that 12pq, and so we can see that 12pq is going to be equal to 48, and we now have to work out what happens to these other powers of 6. And I have grouped everything together there. We've got p squared minus 2q times 6 to the power of 2/3, as I have underlined in red. And then underlined in green, I have got 6q squared minus 2p times 6 to the power of a third, because you'll notice here that you've got q squared times 6 to the power of 4/3, which is 6 times 6 to the power of 1/3, and that's what I've got in the green underlined brackets here, plus 12pq equals 48 plus 20 lots of 6 to the power of 1/3. And you will see that on the left hand side I've got p squared minus 2q lots of 6 to the power of 2/3, but there is no 6 to the power of 2/3 on the right hand side, so p squared minus 2q equals 0. And you will see that on the left hand side we have 6q squared minus 2p lots of 6 to the 1/3, and on the right hand side we have 20 of that, so that 6q squared minus 2p is equal to 20, which means that 3q squared minus p is equal to 10. And we have 12pq equals 48, so that PQ will equal 4. And we notice that p squared minus 2q is equal to 0. P squared has to be positive, and 2q must also be positive, because when it's subtracted from a positive number, it gets you 0. And if PQ equals 4, I think we can fairly clearly see that 2 squared minus 2 times 2 is 0, and so that P equals Q, which equals 2, and so that A equals 2 times, so a to the power of a third, and so that a to the power of a third is 2 times 6 to the power of a third, b to the power of a third is 2 times 6 to the power of 2/3, and that produces our two final answers, that a equals 48 and b equals 288.